Hi, my name is Chelsea Clifford. I'm a postdoc at Iowa State University in the Department of Agricultural and Biosystems Engineering. Today I will present some ideas and initial findings on how the effect of tile drainage for row crop agriculture on streams in the U.S. Midwest compares to more thoroughly conceptualized urban stream syndrome. The images here are of the tile drain installation in Mississippi and of water main installation in Cary, North Carolina. Before I came to Iowa State, I had the privilege of doing my PhD research at the Duke River Center with some excellent urban aquatic ecologists, where I got used to thinking of cities as the quintessential human-modified hydroscape. Many SFS attendees will be familiar with Walsh et al.'s 2009 concept of urban stream syndrome and subsequent work. As a quick, oversimplified reminder, generally, in urbanized landscapes, impervious surfaces such as pavement and roofs largely prevent precipitation from infiltrating or evapotranspiring. Instead, impervious surfaces and stormwater pipes shunt water mostly sideways, usually quickly and directly into streams without pre-processing by the soil. Urban streams turn flashy, with quicker, stronger discharge after rainfall or snowmelt. This change in flow alters a suite of physical and chemical parameters in streams, such as increased channel incision, temperature, nutrients, and pollutants, which in turn affect biota. Iowa cornfields feature a lot less pavement than cities. However, industrialized row cropping also often features a subterranean network of pipes, or tile drainage, and these drainage tiles also shunt water sideways and reduce the volume of soil through which water percolates. In case you are not familiar with tile drainage, at left is a cross-section of how it works. Pipes laid a meter or two below the soil surface keep the groundwater table from getting high enough to damage crops. As shown in the diagram at top right, these tiles form a branching subterranean network that empties into streams without opportunities for soil processing and slowing of drainage water once the water enters the tiles. These drainage tile networks alter hydrology, soil, and plant growth to a degree visible from space. The lines in the aerial image at lower right from Ohio are drain tiles, with more consistent spacing of the tiles at the top. Much of the world in the U.S. has some tile drainage in wetter cultivated places, but the U.S. upper Midwest is an epicenter, as this map shows. Upwards of 80% of land area in the darkest blue counties is tile drained. As in cities, this drainage infrastructure is worth many billions of dollars, and much of it is due for replacement. So there's opportunity for input and change here in this area that creates such problems downstream in the Gulf of Mexico. One way I've had to flip my thinking since moving from North Carolina to Iowa is that I thought of cities as maximum land alteration, but urban development tends to be patches networked by threads that fragment a landscape matrix of, in the Piedmont of North Carolina, mostly second growth deciduous forest, as well as some row cropping. However, here in Iowa, the altered landscape and hydrology of tile-drained row crops is the landscape matrix. This is really just a water alteration-oriented way of restating the well-known landscape alteration situation in the Midwest. Modern agriculture has removed over 99% of native tallgrass prairie and wetlands in Iowa. All of this got me to thinking about if agricultural and urban environments could learn from each other per hydrologic management of how those landscapes drain. I am, naturally, not the first to notice that drainage may have similar effects wherever it occurs. Kristen Bland et al. Published a review on the effects of agricultural drainage on aquatic ecosystems in 2009, the same year that Chris Walsh et al. Published their paper on urban stream syndrome. However, I think it's still worth bringing research on these two landscapes together more than has, to my knowledge, been done so far. For example, there are many analogous problems and opportunities around urban streams and agricultural streams affected by tile drainage, and I think it's worth noting these, as either system may be able to learn from how the other system has handled its analog. As we've established, both systems have underground pipes draining them. Both deal with seasonal anthropogenic vegetation debris in the form of grass clippings and leaves of street trees in cities, and of corn stalks and other non-grain portions of crops in agriculture. I figured that aquatic corn stover might be the least believable to coastal folks, so this photo is of what flood debris looks like in Iowa. Those are corn stalks. Our sewage comes from livestock. It often sits in lagoons or is spread on fields. Both urban and agricultural land have users and owners who may be resistant to change in land use, including that by a shared non-human resident, beavers. Both urban and agricultural streams provide recreational corridors, though agricultural streams are, as Grace Wilkinson once pointed out to me, less recognized as valuable where they are rather than just as problems downstream. Both respond to environmentally perverse incentives and to regulation. Both have yielded novel restoration and mitigation techniques, such as green roofs and saturated buffers. Both have lost natural vegetation, soil, and sensitive biota. Both present public health problems and have disproportionate impacts on sensitive human populations. Both present opportunities as well, especially given that existing stormwater and agricultural drainage infrastructure generally need repair now. Now for a bit more of a specific case study. I went looking for a data set that would help me assess if the flashiness paradigm from urban stream syndrome is also relevant for tile drainage. As part of the National Aquatic Resource Surveys, the USGS and EPA have been monitoring streams in the Midwest. Of these monitoring sites, 28 are co-located with USGS stream gauges, and 25 of those had complete daily measurements for the water year 2013 when a round of monitoring occurred. Thus far, I have not been very successful in my structural equations modeling based on this dataset. This model includes transformed versions of watershed variables, basin area, percent cover of wetlands, row crops, and estimated tile drainage, as well as in-stream transform dependent variables of the Richards-Baker flashiness index and nitrate concentration. Unsurprisingly, tile drainage increased with row cropping, and nitrate increased with tile drainage. More interestingly, nitrate concentration appeared to depend primarily on tile-drained crops rather than total row crops. Meanwhile, wetlands and row crops overall mildly decreased flashiness, while tile-drained row crops had an insignificant positive effect on flashiness. Row crops had a high inverse correlation with impervious surface coverage, so the apparent negative effect of row cropping overall on flashiness most likely reflects a positive effect of impervious surfaces on flashiness. This correlation may also explain why the percent row crops does not have a significant effect on nitrate. It may be easier to tease apart the effects of tile drainage, non-tile drained row crops, impervious surfaces, wetlands, and other natural ecosystems if I expand this analysis to include more heterogeneous regions and thus more samples in future. Biological data and a new year of sampling are now available as well, so I hope to expand this analysis further down the causal chain into biotic effects. So, in conclusion, drainage infrastructure is an issue and an opportunity for management of both urban and agricultural streams. It appears that the two share some mediating hydrologic, physical, and chemical processes as well. More scientific and management crossover between the two systems could prove fruitful. Finally, thank you to the USGS and EPA for the data sets analyzed here, which I had no part in collecting. For discussing these ideas with me and sharing your new ones, thanks also to Iowa State University, especially my boss Matt Helmers for letting me do this, as well as Grace Wilkinson and Jan Thompson, plus the Duke University River Center, especially alums Kendra Kaiser and Krista Kelleher. I will be around for the moderated discussion, and also please feel free to contact me directly with questions. Thank you for watching.